All right, welcome back. Today, we're putting on our detective hats and stepping into the lab to solve a classic whodunit. But our mystery isn't about a person, it's about a molecule. We've got an unknown substance, and it's our job to figure out its true identity. So let's get right into it.
Okay, so picture this. This is our crime scene. We've got a beaker filled with a clear, colorless liquid. I mean, it could be anything, right? Water, alcohol, something way more interesting? That is the central question of our investigation. And to find the answer, we need to start gathering some clues.
And that is exactly the plan. We're going to approach this systematically, just like a real detective would, piecing together the evidence, clue by clue, until the truth just has to reveal itself.
Now, every good investigation starts with what you can observe right there at the scene. Before we bring in any of the high-tech gear, let's just use our senses to gather some of those initial clues about our mystery liquid.
That's right. You'd be surprised, but the first step is often as simple as carefully noticing the smell. A molecule's scent is a physical property, and it can tell you a surprising amount about its chemical family.
So, what are we sniffing for exactly? Well, different chemical families have these signature smells. If you get a really unpleasant whiff, kind of like ranted butter, that points towards something called a short-chain aldehyde. But a more pleasant, rosy smell, that could be a long-chain one. And that sharp, super familiar smell of nail polish remover, that is the classic sign of a ketone. Let's just say our liquid has a sharp, slightly unpleasant smell. Okay, clue number 1 logged.
Next up, another piece of physical evidence, the boiling point. Now, this chart might look a little intense, but the idea behind it is actually pretty simple. Think of molecules as having different levels of stickiness. Some molecules, like alcohols, are really sticky, so they have high boiling points. Others, like alkanes, they're not sticky at all, so they have low boiling points. Our suspects, the aldehydes and ketones, they're moderately sticky. They fit right there in the middle. And what do you know? Our unknown's boiling point falls right in that middle range. The plot thickens.
Okay, so we have a suspect profile starting to form, a compound with a sharp smell in a medium-range boiling point. But physical clues can only take us so far. It's time to head to the lab and run some chemical tests to really confirm our suspicions.
And this is the first, most critical question we have to answer. The smell and the boiling point suggest our molecule belongs to a specific family called carbonyls. That's the family that includes both aldehydes and ketones. But suggestions aren't proof. We're detectives. We need definitive evidence. So how do we get it?
We use a special tool called Brady's reagent. You can think of it like a chemical trap that's designed to catch one thing and one thing only, a carbonyl compound. If our unknown is what we think it is, adding this reagent is going to trigger a very visible reaction. A solid will literally form right before our eyes, and we'll know we're on the right track.
And we get a result. A vibrant orange solid appears in our test tube. This is our first major breakthrough. We can now say with 100% certainty that our unknown molecule is a carbonyl compound, and that is huge because it narrows down the possibilities dramatically.
So we've identified the family, but that leaves us with 2 main suspects, aldehydes and ketones. And the crucial difference between them, the thing that lets us tell them apart, it all comes down to how they handle a chemical attack. Aldehydes are kind of fragile. They can be easily rusted, or what we call oxidized. Ketones, on the other hand, are much tougher. They resist that kind of change. This chemical vulnerability is the key.
All right, we have our 2 prime suspects lined up. So now we need a test that one will pass and the other will fail. We need to exploit that key difference in their reactivity to finally, once and for all, distinguish between an aldehyde and a ketone.
The procedure here is just beautiful in its simplicity. We're going to use a mild oxidizing agent, one that's just strong enough to react with a fragile aldehyde, but way too weak to bother a tough ketone. If we see a reaction, we've found our culprit. If nothing happens, well, we know it has to be the other suspect.
You guys, this is the aha moment. These tests give you undeniable visual proof. Using something called Tollin's reagent, an aldehyde creates this absolutely stunning silver mirror right there on the glass. Another test, with Felling solution, it produces a brick red solid. There is no ambiguity here. It's a clear yes or no.
So we run the Tollin's test on our unknown, and would you look at that? A perfect silver mirror. The evidence is conclusive. Our mystery molecule is an aldehyde. We've officially eliminated ketones from our inquiry. Case closed? Not quite.
See, we know it's an aldehyde, but which aldehyde? There are a ton of different ones.
to pinpoint its exact structure, how many carbon atoms it has and how they're all arranged, we need to bring in the heavy machinery. We need a molecular fingerprint.
And to get that fingerprint, we use a technique with a kind of intimidating name, carbon-13 NMR spectroscopy. But seriously, don't worry about the name. Just think of it as the forensics lab's most powerful scanner. It doesn't look at the whole molecule, it looks specifically at the carbon atoms that make up its skeleton, and that gives us a unique, undeniable fingerprint.
So how do you even read this fingerprint? Well, it's actually surprisingly straightforward. The number of distinct peaks, those vertical lines you see, tells you exactly how many different types of carbon atoms are in the molecule. So if you see 3 peaks, that means there are 3 unique carbon environments. Simple as that.
The key thing to get here is that every single molecule creates a completely unique pattern. The number of peaks, where they are on the chart, it's all determined by the molecule's exact structure. No 2 different molecules will ever have the same NMR fingerprint, and that's what makes it our final definitive piece of evidence.
So, we've gathered the physical clues, we've run the chemical tests, and now we've analyzed the molecular fingerprint. All the evidence has been collected, and it is all pointing in one direction. It's time to unmask our molecule.
The NMR spectrum for our unknown shows 3 distinct peaks. That tells us it's a 3-carbon aldehyde. The evidence is absolutely irrefutable. Our mystery liquid is propanal. And just look at how we did it. We started with basic observations, smell, and boiling point. We confirmed it was a carbonyl with Brady's reagent. We proved it was an aldehyde using that beautiful tolerance test. And finally, the NMR spectrum gave us the unique 3-carbon fingerprint that just sealed the deal. It's a perfect chain of logic.
So, why does this all matter? Well, because identifying a molecule, giving it its name, unlocks its entire story. We now know our propanal can be oxidized to form propanoic acid. We can predict all of its other reactions. The identity tells us everything about its behavior.
We've cracked the case of the unknown liquid. But this process, this observation, testing, and deduction, that is the very heart of chemistry. It reminds us that every substance in the world has a hidden identity and a unique story just waiting to be told. The only question is, what will we uncover next?